Hello dear students, welcome you all for transmission and distribution class. So continue with the underground cable. Today we will see the grading of the cables. Grading of the cables, mainly it is having two different types of grading. One is capacitance grading, another one is interstage grading. Today we will go with the capacitance grading. The process of achieving uniformity in the dielectric stress by using layers of different dielectrics is known as capacitance grading. So in capacitance grading, the homogeneous dielectric is replaced by a composite dielectric. The composite dielectric consists of a various layers of the different dielectrics in such a manner that relative permittivity ER of any layer is inversely proportional to its distance from the center. Under such conditions, the value of potential gradient at any point of dielectric is constant, is independent of its distance from the center. In other words, dielectric stress in the cable is same everywhere and the grading is ideal one. However, ideal grading requires the sum of infinite numbers of dielectric, which is impossible task. In practice, two or three dielectrics are used for the decreasing the order of permittivity. The dielectric of highest permittivity is being near to the core. So the capacitance grading is explained in the figure, this 11.15. You can see this clearly. There are three dielectric of outer diameter D1, D2 and capital D with the respectively permittivity of epsilon 1, epsilon 2, epsilon 3. Okay, the permittivity is such that epsilon 1 is greater than epsilon 2 is greater than epsilon 3. Means epsilon 1 is the highest permittivity and the last one is the least permittivity. So the three dielectric are worked as the same condition. Then stress is given by 1 over epsilon d is equal to 1 over epsilon 2 d1 equal to 1 over epsilon 3 d2, or e1 d, which is equal to epsilon 1 d is equal to epsilon 2 d1 is equal to epsilon 2 d2. You can see these things clearly there. Potential difference across the inner layer is given by v1 is equal to integration of d by 2 to d1 by 2. You can see here in this figure it is very clear. Outer diameter is d1, d is the diameter of the core, d1 is the first layer, d2 is the second layer and capital D is the third layer. Fine, then v1 is given by the integration of d by 2 to d1 by 2, means from the core to the first layer into g dx is equal to whatever g value we will put, that is q by 2 phi epsilon naught epsilon 1 x, that is. So after solving that one we will get, so v2 is g max 2, because v2 is the potential across the layer v2 and the third layer. So v2 and v3 is given by g max by 2, g max by 2, that's same d1 log natural d2 by d1. In third case v3, that is g max by 2 d2 into log naturally logarithm t by 2. You can see these things very clearly, means from which layer to which layer that is to be taken. Then total v is given by v1 plus v2 plus v3, or if you take the g max by 2 as common, we will have these equations. So if the cable has a homogeneous dielectric, for the same values of g, d and g max, permissible potential difference is given by g max by 2 d log e d by d, that is the homogeneous dielectric is used for the same value. Obviously V is greater than the V dash, means if it is a composite dielectric, it will give you the more voltage compared to the homogeneous dielectric for the given dimension of the cable, and graded cable can be worked at the greater potential and non-graded than the non-graded cable, means graded cables can be used for with the same size and capacity, can be used for more values or more potential than the homogeneous one. Alternatively, for the same potential of the size, graded cable will be the less that of the non-graded cable. The points to be noted are, as the permissible values of Gmax are peak values, therefore all the voltages in above expressions should be taken as peak values and not the RMS values, and the maximum stress in the three dielectrics is not the same, then V is equal to G1 max by 2 d log e d1 by d. Same thing g2 max by 2 or d1 log e d2 by d1. Same g3 max by 2, means here g max is not same, then we need to take like this. It's not simply is G max, it is G1 max, G2 max, G3 max. Okay. So the principal disadvantage of this method is there are few high grade dielectrics of reasonable cost whose permittivities are vary over the required range. So we will solve one problem here. Here the problem is given with a single core lead sheathed cable is graded by using three dielectrics of relative permittivity 5, 4 and 3 respectively. The conductor diameter is 2 cm, overall diameter is 8 cm, that is small d is uh, 2 centimeter and capital D is 5 centimeter, 8 centimeter. The dielectrics are worked on the same maximum stress 40 kV per centimeter. Find the safe working voltage of the cable. What will be the value of the safe working voltage of an for an ungraded cable, assuming the same conductor overall diameter and the maximum dielectric stress? So we need to calculate the here safe working voltage for the both graded and ungraded. We will write down the things given. In graded cable, we know epsilon 1 D is equal to epsilon 2 D1, epsilon 3 D2. If you put that one, we can find out the D1 as well as D2 easily. Okay, once we find out D1, D2, we will go with the permissible with equations G max by 2, D natural logarithm D1 by D. These equations we are knowing. Put all the values, we will get a value of 20 kV, and here the 20 into multiplied by the 4.094, so obviously we will get 81.808 kilovolt. For a safe working voltage is given by, that is RMS value, that is divided by root 2. If it is ungraded cable, the only thing is we need to take D and small d and capital D. So G max by 2, we will put that one, we will get a 55.4 kVA. If the safe working voltage is 39.2. So it is very clear that for the same size of the cable, if it is the ungraded one we are using, we are able to use still on 39.2 kV only. But if it is graded one, we can go up to the 57.87 kilovolt with the same size of the cable. This is what the advantage of the grading. So the same type of another problem is given here in 11.13. A single core lead sheathed cable has a conductor diameter of 3 cm and diameter of the cable is 9 cm. The cable is graded by using the two dielectrics of relative permittivity 5 and 4 respectively, with corresponding the safe working voltage stress 30 kV per centimeter and 20 kV per centimeter. Calculate the radial thickness of the each insulation. Here G1 max, G2 max is given. So we need to solve it like this. We know G1 max is proportional to 1 over epsilon 1 D. G2 max is 1 over epsilon 2 by D1. If you divide it, you will get G1 max by G2 max is equal to epsilon 2 D1 by epsilon 1 D1 D. So you will get D1 as 5.65 centimeter. So radial thickness can be calculated by D1 minus D by 2. You will get 1.312 centimeter. Radial thickness of the outer dielectric can be given by D minus D1, that is we will get 1.68 centimeter. So permissible peak voltage of the cable is given by, we will put all the values here because G1 is 30, G2 is 20. With these equations we will get a 54.71 volt as the permissible voltage. Same one, another problem is there, you can solve by your own this problem. Here it is given with 66 kV core lead sheathed cable is graded by two dielectrics of relative permittivity 5 and 3 and thickness of each is being 1 centimeter, core diameter is 2 centimeter. So you can solve this problem by your own, the same as the previous one. So solve all the three problems once and write down this derivation of the capacitance grading. Okay, if you find any difficulties you can call me, and in the next class we will go with the intersect grading. Okay, fine, thank you.